So on your screen right now, I'd like to start off with this image. It sort of captures a lot of what I've done and what I continue to do in my research. This is an image of a lighthouse in the northern part of Lake Michigan. It's very, very far offshore, and it's taken right in the dead of winter. And I show this picture because we sometimes like to joke that it's an ideal place for a student winter internship program. I'm actually joking about that. This is not a safe place at all for students to be in the wintertime. But it is one of the best research sites for doing freshwater research on the entire planet. You really can't get much further offshore than these old lighthouses. And one of the fun things we did is we turned the top of this lighthouse, or we put on top of this lighthouse, an evaporation station. As you'll learn more in my talk, measuring evaporation is one of the key things we do to understand why water levels on the Great Lakes fluctuate or why they go up and down. So I'm going to start off with a little bit of background about myself and some of the general research that my group does. And then I'm going to focus on two specific research topics. The first is work that we do in understanding coastal water quality and connections between coastal water quality and human health. And then I want to talk about another area of research that's really sort of, for lack of a better term, exploding right now. That has to do with understanding the water balance or the water budget of large lake systems. This has become extremely important recently, particularly here in the Great Lakes region, because Great Lakes water levels have reached record highs over this past summer. Lake Erie and Lake Ontario in particular exceeded their all-time record highs dating back to 1860. So that's 150 years worth of record. We just broke all-time record highs. So this has been a really hot topic of research. We've been doing a lot of work with the media, newspapers, and the press to tell this story. And that'll leave you with just a few final thoughts of some of the work we're doing. So to dive in, just a little bit more about myself for what it's worth. I live here in Ann Arbor with my wife and my twin sons. They're a little bit older than this right now, but they're kind of a handful. This is us along the Huron River here in Ann Arbor. And I love blending my love for the Great Lakes and my research with the Great Lakes with the kids. Here we are on the ice on Lake Michigan, not far at all from that lighthouse I showed you earlier. This was supposed to be spring break in April of 2014, but as you guys might remember, and many of you remember, there was an Arctic polar vortex deformation. Yeah. And so even through mid-April, there was about 3 feet of ice on the shoreline of Lake Michigan. So this is a picture that connects a little bit with what I do with my family. I also want to point out that I've been very fortunate to have a very strong team of collaborators and scientists that I work with. Here are a lot of folks that I worked with at the NOAA, the National Oceanic and Atmospheric Administration, Great Lakes Environmental Research Laboratory. It sounds like some of you are familiar with that group and might even know some of these folks. But there's a great group of scientists, students, postdoctorate fellows that I've worked with both at NOAA and here at the University of Michigan. And the vast majority of the work you're going to see is a testament to their hard work. So, quick snapshot of some of the broad things we do, just to tie it all together. I talked about, and I will talk more about the work we do on large lake water balance modeling. One of the, what I would call, endpoints of that research, or decision-making level response variables that we do all this work for, are decisions like the one represented on this slide that have to do with hydropower management. So here in the Great Lakes, one of the largest, or the largest hydropower facilities are the ones along the Niagara River near Niagara Falls. So I'm presuming that you might be able to see my hand. Can you guys see my hand moving around the left panel there? Just a couple of head nods from any of you would be helpful. Can you guys see my hand? Yep, okay, yeah. Great. So in this left image, here we are looking at Niagara Falls. And this bottom horseshoe right here, this is on the Canadian side, and then the smaller falls area is the United States side. What's key about this is that there are large pipes that take water from this upstream side of the falls near the cities here, and they run underground. And if you can see, they take that water. If you look at the top of this image way up here, that's a storage pond. Water gets transferred to that storage pond. It's really like a huge lake, and then runs through turbines like the ones you see on the right-hand side of this screen. So where my hand is right now, this is the Ontario Power Generation hydropower facilities. This is way down on the Niagara River. And in fact, if you look upstream from this point, you can see the mist at the top of the page. That's the fall. So we're looking at the same area just from two different perspectives. I point this out not only because it's a cool image, but a lot of the work that we do in understanding the Great Lakes has direct impacts on the shipping industry, on the recreation and tourism industry, and indeed, in this picture right here, on the hydropower industry as well. There are also connections with what we do to massive scale processes involving ice cover, wind, wave formation. This image that you see right here sort of is a snapshot of a lot of what we do. It's a satellite image of Lake Erie in the wintertime. So if you follow my hand, actually it includes several lakes, my hand up here is outlining the shoreline of Lake Huron. And what I find fascinating about this image is that my hand is along the shoreline here. That crack you see, that's a break in the ice cover along the entire surface of Lake Huron, tens of kilometers wide. It's a huge surface area. Water flows from Lake Huron down through Lake St. Clair, and you can see then here on Lake Erie this big patch of ever-moving ice cover. I point this out, again, not because it's just a cool satellite image, but a lot of what we do in our research is we try to develop data sets and computer models that can simulate and represent the processes that you're seeing here on the screen because they affect surface temperature, they affect coastal habitat, they affect things like lake evaporation, all of which we're trying to understand. And then finally, here's an image, again, sort of a summary image showing an area of my research. This is a picture taken from the coastal areas of North Carolina where I did a lot of my graduate school research, indicating that there's a water body that is closed to shellfish harvesting because of water quality concerns. And that's yet another area of research that we do. So with that as big picture context, I want to dive into two specific areas and sort of give you an in-depth look at how we go about answering some of the questions that are posed about uncertainty, about variability, about modeling. So let's start off with coastal water quality and human health. And when I came to the Great Lakes, we transferred some of our research from coastal marine areas to freshwater areas. This is actually an image of the beaches right along Lakeshore Drive in Chicago. So the key point here is that these water quality issues are not just about the marine coasts and shellfish and oysters. They also have to do with beaches, both in the freshwater and the marine environment. So the key point here is that the safety and the health the safety and the water quality of these beaches is a big concern. There are limits posed on when people can enter these beaches based on water quality standards. And so one of the important parts of the water quality standard program is the testing methods used. So when I was doing research in North Carolina, there was a lot of concern about variability and uncertainty in different water quality testing procedures. So this image that you see here on the left, that's a methodology that has been used for decades, going back to the early 1900s, called multiple tube fermentation. Essentially what you do is you take a water quality sample, divide it up at different dilutions into a bunch of different tubes, let those tubes incubate overnight, and then you count the number of tubes that are either positive or negative, and you can figure out an estimate of the concentration that was in the original sample. Well, since then, things have evolved. A lot of you have probably done an analysis like this is a membrane filtration technology, where you take a sample, run it through a filter, let it incubate over a 24 or 48-hour period, and you count the number of colonies that form, and that's intended to be an indication of how many bacteria there were on the plate in the first place. Well, since then, technology has continued to evolve, and now one of the state-of-the-art methods for doing this type of fecal coliform analysis is the pollutant we're concerned with here. The sample is divided up into a bunch of these little cells, and after a period of incubation, the cells in the presence of bacteria will either glow or not glow, and you can count the cells that glow. Here's the key point. For all of these methods, there are mathematical and statistical models that relate what you're seeing on the screen in terms of either the number of colonies that form or the number of cells on the right that turn bright yellow, that relate what you see into some estimate of concentration of the fecal coliform or E. coli concentration in the original sample. So what we did in our research here is we actually unraveled all of those statistical models that we used for these methods, and we applied them to a brand new method. So when I finished my research in the coastal areas of North Carolina, a microbiologist from the University of North Carolina, Chapel Hill. His name is Mark Sobsey. He called and he said, "Hey, Drew, can we take our understanding of how these types of technologies relate to fecal coliform concentrations, and can we design an entirely new testing procedure?" The answer, in a nutshell, was yes. What we did is we ended up designing a whole new test kit that's now used all around the world based on the relationship between whether or not a compartment or a cell or a tube of a certain volume and a certain dilution, whether it's either positive or negative, how that relates to the concentration. So what you're seeing on the screen here, on your left, is the bag that we ended up designing. It's called the compartment bag test. It's very simple. There are 5 pouches, each of a different volume. And when people put their water quality sample in that bag, they shake it up, and then they can take the pattern of positive bags on the left and look up that pattern on a table on the right that shows which compartments are either positive or negative, and get an idea not only of the concentration, but most importantly, on the very far right on the table that you see, whether or not there's an immediate threat to human health based on either poor or high water quality. So this was really a lot of fun research. Again, taking kind of boring, geeky statistical models, but turning it into something real and helpful for the real world. Since we started this program, there's actually a company that's been formed around this product called Aquagenex, and they distribute this compartment bag test all around the world. It's used in a lot of different places. We actually published a paper in the journal Science of the Total Environment called the Compartment Bag Test for Enumerating Fecal Indicator Bacteria, Basis for Design and Interpretation of Results. So this is sort of the statistical model behind the bag, but it's used now in Nepal, it's used in Africa, all around the world to help people get a better understanding of whether or not water quality poses a human health risk. So really satisfying work there. And we did a lot of other things with water quality modeling, but I thought that would be an interesting snapshot for you. Now let's shift gears and let's talk a little bit about this work we do on large lake systems and their water balance. So when we talk about a water budget, what we're talking about here is the amount of water that comes into a lake and leaves a lake, just like a bank account and money. But in this case, we're talking about water. Before I go any further, I want to put into perspective the large lakes on Earth. There are about 100 million lakes on Earth. But what I find interesting, and I don't think I've talked about this before, Meg, with you or others, but in recent research we've done, we found that the largest 10 lakes on Earth hold 80% of all of Earth's fresh surface water. So I'll say that again. 10 lakes on Earth, really big lakes, most of the ones you see here, they contain 80% of all of Earth's fresh surface water. The other 20% is distributed among 100 million lakes. So when we think about the research that we do, we really think that it has a pretty big impact in terms of studying how water enters and leaves these large lakes. So what you're seeing here is a table that summarizes Earth's large lakes. These are summarized by surface area, but they're also the biggest ones by volume. So you can see I've got the name of each lake on the left, the country or the countries in which those lakes reside, and then I've got surface area and volume, both in terms of kilometers squared, miles squared, kilometers cubed, and miles cubed. Now, for the research that I'm going to talk about today, if we highlight the lakes that make up the Laurentian Great Lakes right here in our backyard in the central Midwest, we see some cool patterns. The first pattern is that when it comes to surface area, that's middle set of columns here, there's nothing close to the Great Lakes. We're talking about one of the most vast surface area or collections of surface water on the planet. I mentioned earlier about the volume, and the top 10 largest lakes on Earth having 80% of the water. The Great Lakes have about 20% of all the water on Earth, and then together with Lake Tanganyika and Lake Baikal, you see the fourth and the fifth lake down. The Great Lakes, Tanganyika, and Baikal have about half of all the Earth's water. So really massive lake systems here. We're studying one of the largest. This image, that may all sound nice and everything, but this image, like some of the ones I've shown earlier, is trying to relay the complexity of understanding the hydrology of the Great Lakes system. So this is a satellite image, taken in December of 1999, and it's kind of an unconventional view of the Great Lakes. So we're actually looking from west to east across the Great Lakes. So where my hand is, right here, that's actually Duluth. That's the western corner of Lake Superior. So if I move my hand along here, that's the northwest shoreline of Lake Superior. And then if I move my hand along here, that's the western shoreline of Lake Michigan. So we're sort of right about here, at least those of us in this room, right about here in Ann Arbor right now. But I show this image because it shows a lot of different things going on. The first is that when you look at the land surface, there's a lot of snow on the ground, but it's not distributed uniformly. There are places in upper Wisconsin and Minnesota, right through here where there's a lot of snow, places in Canada. But in parts of Michigan and northern Ohio, there's not a lot of snow. When we develop models of the entire Great Lakes system, we have to capture this spatial heterogeneity that you see here. Just like when we capture the ice cover that I showed you earlier on the lakes, we have to represent that as well. One of the other fascinating things that's going on here is the amount of water that's being transferred from the lakes into the atmosphere, and that should be readily apparent on your screen. That's essentially evaporation. Really, it's clouds, but it's going hand in hand with water that is leaving the lakes in the form of evaporation and leaving the basin. That's one of the biggest sources of water loss from the lakes, and it's December when evaporation actually reaches its peak. It's the time of year when there's cold air going across the lakes, and the lakes are still losing heat during that time period. Now, a similar, a different perspective, but on the same phenomenon, is this image right here. What we're seeing here is a lake effect snow event barreling its way across Lake Erie right towards the city of Buffalo. This particular lake effect snow event took place in November of 2014. It ended up dumping 5 feet of snow on the city of Buffalo when it was all said and done. Same process that I showed you in the previous slide when we have water and moisture leaving the lake, entering the atmosphere, but in this case, the snow precipitates as soon as it hits Buffalo, and can really lead to a lot of damage and loss of lives. So when we try to understand these evaporation processes of the lakes, it's not just for understanding the water balance, it also helps us understand meteorological and climate processes like this one that you see here. So one of the things we've learned is the extent to which precipitation and evaporation work in balance across the Great Lakes. What I'm showing here is a summary of what we learned about the Great Lakes water budget, that is all the water that comes into and leaves the Great Lakes. And it really, on the left-hand side, boils down to 3 main components. Runoff, which I'm going to represent with green, overlake precipitation, which I'm going to represent with blue, and overlake evaporation, which I'm going to represent with pink over there. So these 3 major components of the water balance. And so what I'm showing on the left, if you look at where my hand is here for Lake Superior, this is the amount of water entering and leaving Lake Superior just within its own watershed. So for example, we have, these numbers are in thousands of cubic meters per second. So for example, we have 1,600 cubic meters per second of water on average over the course of the year coming into Lake Superior through, this is the green bar, through runoff. Similarly, we've got 2,000 cubic meters per second of water coming into Lake Superior just through precipitation on the surface alone. I'm going to pause there and actually revisit that for a second. The amount of water that comes into Lake Superior through precipitation falling directly on the lake is more than the amount of water that comes in through all the rivers and streams. That's fascinating. There's nothing on Earth like that. Why is that? It's because Lake Superior has such a large surface area. It's the largest single lake by surface area if you divide Lake Michigan and Huron into 2 different lakes. And then finally, this pink bar right here, that's the amount of water that's leaving Lake Superior on average through evaporation. So we have these competing forces on the water balance. Precipitation and runoff tend to drive water levels up. Evaporation tends to drive water levels down. And you can see the same numbers here for the other lakes. For Lake Michigan and Huron, when we combine them into one big lake, Lake Erie and Lake Ontario. So those are the major components of the internal water budget for each lake within its watershed. Now, the other thing we have to study and learn about is water that transfers from lake to lake. So if you shift over to the right-hand side here, this is representing the rate of water flow between the lakes. It's on the same scale as the graph on the left. So, for example, you can see here that the water flows from Lake Superior into Lake Huron at a rate of about 2,200 cubic meters per second. And then as water flows down through Lake Huron, this hand is a little bit hard to control here, sorry. It flows down through the Detroit River and St. Clair River at a rate of about 5,500 cubic meters per second over the Niagara River. That's where those hydropower facilities are that I showed you earlier. The water flowing through there is at 6,300 cubic meters per second and then out through the St. Lawrence River at a rate of, on average, around 7,000 cubic meters per second. Again, I want to pause and point out that is an extraordinary amount of water. By the time the St. Lawrence River, which flows all the way out to the Atlantic Ocean, by the time it gets there, the average flow rate, it's accumulated so much water that the flow is around 14,000 to 15,000 cubic meters per second. And guess what? That's the same annual average flow rate as the Mississippi River. So the Great Lakes' entire drainage area is transporting just about as much water on average as the Mississippi River Basin. So those are the two really biggest drainage areas off of the continent of North America. Really important context for us as we study the Great Lakes. So what's some of the exciting research we've been doing to try to understand this water balance better? Well, one of the things we've done is we've partnered with the commercial shipping industry in the Great Lakes. So remember how I showed you earlier an image of a lighthouse where we installed an evaporation station? Those evaporation stations were great on the lighthouses, but they were fixed. There was 1 point, or 5 points actually, across the whole Great Lakes where we studied evaporation. What we then did is we partnered with the commercial shipping industry, and this boat that you see right there on the screen is the Whitefish Bay. It's one of the big vessels that crisscrosses the Great Lakes, and way up there in the bow, on this yellow mast that you see, is one of our stations. We installed an evaporation station on the bow, so that collects data that crisscrosses the Great Lakes almost all year round, from Duluth all the way down to Cleveland, back and forth continuously, collecting unbelievable evaporation data across the Great Lakes. So really cool project that we have going on there. We've also done a lot of work to understand and to model what happens on the land surface better, and that's to get a better understanding of that runoff variable that I talked about earlier. So what you're seeing here is work that we did over the past few years to improve what I would call land surface models. These are computer models that take precipitation that falls on land surface and try to turn it into runoff through all the rivers and streams. These white lines that you see on the left over here, those aren't rivers and streams. Those are boundaries of watersheds or catchments. And that's what we represent, or those are the areas that we try to represent in an old model, which is what you see on the left. The new way of doing things is to divide the land surface into every single river, stream, and segment possible, and that's what you see on the right. And that's the new model that we just developed over the past couple of years. The black dots and the red dots that you see on the right, those are actually the location of, the red dots are United States Geological Survey flow gauges, and the black dots are Canadian Hydrographic Survey flow gauges. The black ones are in Canada, the red ones are in the United States. And we can actually use those gauges, the information they're collecting on flow, within our model to improve how it's simulating and forecasting flow over time, and ultimately give us a better picture of the overall water budget of the Great Lakes. So one of the fun things we get to do is put all this together in our scientific research and answer important questions. In the late 1990s, water levels went down on the Great Lakes a lot. You can see here in this particular image that from a paper we published in Science. On the bottom here, we're looking at water levels. The dark green line is water level on Lake Michigan, Lake Huron, and the light green line is water level on Lake Superior. So water levels going along here in the 1980s, 1990s, and then, whoa, they crash right here in the late 1990s. The letters A and letters B represent months where water levels hit record lows. And I know it's interesting, we were just talking at the beginning, I was just talking at the beginning of this talk about water levels flooding right now, but back in 2013 and 2014, people were concerned about climate change and low water levels. So at the time, there were a lot of questions about why water levels were so low. What we did in this paper is we said, hey, it looks like surface water temperatures, which is on the top panel here. So the dark blue line is Lake Michigan Huron. The light blue line is Lake Superior. And what we found is that surface water temperatures in that time period jumped up a lot. They went up by about 2 degrees Celsius. Now, even if you aren't a physics major, to take Lake Superior, Lake Michigan, and Lake Huron and raise the surface of them by 2 degrees Celsius on average for that entire time period is a tremendous amount of energy. So something happened there that we did a lot of research on. But the important point here was that provided the best explanation for this jump in evaporation that we saw during that time period, and ultimately the loss of water and lower water levels during that time period. So kind of a fun way to tie together a lot of these big observations that we make about the Great Lakes into a really important story. I think I have enough time. I just want to mention that one of the things that was about to happen before we published this work was there was a lobbying group on the Great Lakes that was arguing for putting flaps, for putting control structures in the river between Lake Huron and Lake Erie. And what those flaps were going to do is they were going to slow down that river flow that I showed you earlier and artificially raise water levels on Lake Michigan and Lake Huron. Luckily, they didn't do that because, well, we convinced them through this paper and through a lot of research from other folks that climate change and the variability of the climate system is what was driving this, and that water levels may, in fact, in the future go up, and that's actually what happened. So it's a good thing they didn't put those flaps in. Sure enough, as water levels surged over the next few years, leading to where we are right now, there was a lot of concern. We wrote an article that ended up being on the cover of this magazine, EOS, which is one of the more popular Earth and Space Science journals. And this is sort of an iconic image. Again, going back to Chicago, this is water crashing over the iconic bike path that sort of goes along the shoreline of Chicago as water levels began to rise again. So I'll leave you with just a few parting thoughts on sort of where our research is and some other interesting things that we're doing. I showed you a slide early on about ice cover on Lake Erie. One of the more fun recent projects we've done has been trying to predict the date of ice onset on a very interesting part of Lake Superior called the Apostle Islands National Lakeshore. Here's an image from inside that National Lakeshore, one of the caves that form. This is nestled right on the shoreline of Lake Superior. And in the middle of winter, these ice caves form, and they're a very popular tourist destination. The Apostle Islands National Lakeshore folks wanted us to develop a model that could help predict when ice would be thick enough and safe enough for people to walk out on the lake and access these caves, and that's something that we did in our research. We also did a lot of work over the past few years, taking what we learned about water levels and trying to do a better job of conveying that to the public. So this is a product that you're seeing that was developed by an informatics major here, right at the University of Michigan. It's called the Great Lakes Water Levels Dashboard. It's an online, interactive, Adobe Flash-based tool where you can click and zoom and do all kinds of things with water levels. What I'm showing you now is water levels on Lake Michigan Huron going back to 1995. So you see those light blue dots? Those are monthly average water levels. And we developed this tool not just to look at lake water levels and see how they go up and down over time, but with a click of a mouse button in this tool, you can add to this. Oops, sorry, not yet. This is the paper that we wrote about this tool in the Journal of Environmental Modeling and Software, and sort of it's fun anytime we do this research to turn it into a peer-reviewed paper. Back to the dashboard. With a click of a mouse button, we can add in a whole new data set. This is ice cover on Lake Michigan and Huron. So we often get asked about the relationship between water levels and ice cover. And what you can see here is, we talked earlier about how in the late 1990s, surface water temperatures went up. Well, you can see how ice cover went down for a very long time period. It was very, very low throughout this entire time period. A lot of that was because lake water temperatures were so high. I talked in the beginning about that Arctic polar vortex deformation in 2014. That led to near record-setting ice cover in 2014 and high ice cover again in 2015. And that coincided with this water level rise that you see here, which is when we had that picture of the Chicago skyline and when evaporation rates went down. Interestingly, a lot of people ask us, well, can you tell us more about the relationship between water levels and ice cover and evaporation? Again, with this tool, with a click of a mouse button, we can add in all that evaporation data we've collected, and now we've got a really cool story that we can tell and even show the public, which indicates that there's a relationship here between when evaporation starts each year, which is usually in the late fall, starts to peak around December, and then as evaporation drops, that's when the lakes are getting really cold. They don't have energy to give off anymore in evaporation, and they start to freeze and turn to ice or form ice. I'd say one of the key things that this project did was that it sort of dispelled the myth that ice puts a cap on evaporation. A lot of people said, well, when ice doesn't form, the lakes must evaporate like crazy. No, the wintertime isn't when the lakes would normally evaporate anyway. Ice doesn't really cap evaporation. It just means that when there's really cold water, but it's not quite freezing, the lakes don't evaporate much and they don't form ice. And this graphical representation really helped people understand that. Finally, I want to show you a cover image of one of my favorite papers on Earth. It's a reflection of people's perceptions on climate change trends and climate variability. And this is a quote by someone who manages one of the water supply systems for New York City. And his quote was, someone asked him about water level projections for 2100, and he said, 2100? 2100 doesn't keep me up at night. What keeps me up at night are things that are happening next week and next month. So this isn't meant to say that planning for 2050 or planning for 2100 in terms of climate change isn't important. It is, but we also need to keep in mind the amount of variability in what we're experiencing with the climate between now and then to make sure we make good planning decisions. So I'm going to leave you with an image here, and if anybody you can guess what it is, I'll buy you some French fries next time you're in Ann Arbor.